Okay, hi everyone again. We are back with this second part of the lecture of today. Aurora, please, this is your part.
Okay, thank you. All right, so I have a few more slides finishing up the spectral reduction portion of the class, the lecture, and then we will do a Kahoot quiz and to try to make it run a bit smoother than last time, I've upped the times on all of the questions, so hopefully that works okay today. And yeah, all right, so I'll share my screen.
Yeah, I'll send you access to the email.
Okay, great. So going back to what I had just said before the break, if you do the correction without an A0 star, you are still going to be left with some sort of residual of the blaze function. So on each order, you're going to have less flux at the edges of the spectrum. And so you'll need to do something to correct for that. And often the way that we do correct for that is just a really simple fitting of a polynomial to the continuum to remove that shape. And so I really want to emphasize throughout this talk that a lot of these observing strategies that I've been telling you about, sometimes you're going to use them and sometimes you're not, depending on what science goal you have. So these A0 stars, they do increase the overhead, but they provide you the best time-dependent telluric correction in the near infrared. So you might want to use these in the near infrared, but people don't normally use these in the visible because the telluric contamination is not as bad, so it's easier to remove. Another reason that you wouldn't want to use the A0 stars is for if you're doing high resolution observations of an exoplanet as it transits in front of the star. It's much more important to observe the exoplanet transiting continuously than it is to get the best telluric correction. So you can't take any of that time that you would be observing the transit and go away and observe an A0 star and come back. And yeah. Oh, yep.
Excuse me, Aurora. You have a question in the chat.
Mm-hmm.
What tools are used most often, I guess, for telluric corrections?
Right, yeah. So the tools that I've seen used most often are the Molecfit, which is this synthetic model. And Molecfit is a publicly available code that anybody can download. So if you do have high resolution observations and there wasn't any A0 stars observed with them, then I would suggest using Molecfit. But for near infrared, I think that the most common way to remove the telluric is with this A0 star strategy. And then I'll talk about pipelines in a second. So, right, the basic procedure would be to observe the A0 star and then remove the telluric spectrum by dividing the telluric spectrum that you get from the A0 star from the spectrum that you observe. Yeah, and so with all of these different things, again, yeah, it just depends on what type of science you're interested in and how you can maximize the amount of science observations that you get done while still having all of the necessary calibration that you need in order to get that science out. So another example of tailoring your observing strategy to what type of science you want to do is whether you take the time to observe these wavelength arc lights or not. And I said before that if you really need a good wavelength solution, so you would need a good wavelength solution for high precision radial velocity measurements. You can't you need to take the time to do these arc observations. But if you don't really care exactly about the wavelength solution, so say you want to observe some sort of broadening of the sodium absorption line, it doesn't matter exactly where the sodium line is, as long as you know which one's the sodium line, then you can measure the broadening. And then you don't have to waste any of your overhead time on observing these arc lamps all of the time. So I thought this was cool these are just screenshots I took from the yesterday's workshop class. And here we have our visible spectrum. And again, the colors don't mean anything, but you can see kind of this nice shape here. This is an A-type star, so we're going to get more flux in the blue. And here's our near-infrared spectrum of the same object. And you can see the exact water features that you saw in the telluric spectrum. So there's this big water feature here and a big water feature here. And so let's go back to the telluric spectrum. And you can see that it really looks almost exactly the same as what we're showing here. Here's our water feature at 1.1 micron and our second water feature at 1.4 microns. So you can see just how much the telluric absorption affects our near-infrared spectrum. Okay, so now that we have done most of the steps, there's only a few things left, and it's kind of up to you or up to the user or up to the pipeline that you're using, whether they do these steps or whether these steps are even necessary. But to get a single spectrum that is kind of most what you would assume that you would get out of a spectrograph, just a single wavelength versus flux array, oftentimes the orders are combined. And the way that they do that is they create a single spectrum that is spaced with the resolution of the instrument, and then they interpolate the values from each order onto that uniform spectrum. And you can, in the places where the orders overlap, you can average those together. And so you get then one single nice spectrum. So here's a spectrum from HARP's spectrograph. And you can see basically it goes, oh, sorry, actually, I think this is, I forget if this is Carmena's or HARP's, but it goes from just blueward of 5,000 angstroms to just past about 7,000 angstroms. And it's just one single continuous spectrum. And the last thing that people often do during the reduction process in the post-processing is they correct for cosmic rays. So cosmic rays are just high energy particles, and they're streaming through kind of Earth's environment. Sometimes they're coming from outside of the solar system. Sometimes they can come from the sun. And every once in a while, you're going to get a cosmic ray that hits your detector. And when the cosmic ray hits the detector, you get a huge amount of energy release because these are high energy particles. And so you get something like really nice, you'll have a really nice continuum, and then you'll just get a huge amount of flux at one random point. And those are just from cosmic rays. And in order to reduce the number of cosmic rays you get, you don't want them to be all over the place. People try to keep exposure times pretty low. And so instead of just doing, say you need to do an exposure time of an hour to get a nice spectrum, instead of just doing a single exposure time of a full hour, what people will normally do is they'll do multiple exposures of, say, 10 minutes and then add them up in order to reduce the number of cosmic rays that hit the detector in each exposure, because it's easier to correct if there's only a single or a two cosmic rays and you have multiple exposures. So that way you can see, okay, in this exposure, I don't have anything here. But in the next exposure, I have a huge amount of flux here. So we know that this can't be the star changing at this short amount of time for this huge amount of flux. And so you can easily compare one exposure to the next exposure and see if there's a random increase in flux in 1 pixel. And this is basically, you can tell that this is caused by a cosmic ray. And so then this is really easy to get rid of. You can basically just kind of mask out this pixel and interpolate over it and get rid of the cosmic ray that way. Okay, so now that I've kind of I've gone through all of the steps that are normally taken to do the reduction, I did want to say that oftentimes you don't need to do all of this yourself. You don't need to write the code that does the bias, does the dark combination, and then subtract the dark from every image, and then divide by the flat and extract the flux. There's usually, most telescopes these days will have a pipeline that will do this for you. So for example, the HARP spectra that we downloaded yesterday, those had been already reduced. And so that has already been run through the pipeline. The Carmena spectra, again, they had already been reduced. They had already been run through the pipeline. And what you end up getting is the already reduced spectrum. But it's really good. I think it's still really important to go over all of the steps that they take through the pipeline so that you know why, if, for example, you have a slight amount of shape in some wavelength regions, you can say, oh, well, that's probably because the blaze function wasn't removed perfectly. Or say, for example, you have lots of absorption and you don't know where it's coming from. You can say, oh, well, the pipeline didn't correct for telluric absorption, so this must be from Earth's atmosphere because I know my star doesn't have water in it, or something like that. It's really good to know all the steps so that you can tell what's happening in the spectra. And also, it's good to know all of the steps because different telescopes will publicly release data at different stages of post-processing. So you need to be able to, if they say, oh, we're releasing spectra that have been extracted, but none of the post-processing steps have been done. Now you would know, okay, that means that I have 1D spectra, they have a wavelength solution probably, but they're all going to have a blaze function still on them. There's going to be cosmic rays in there. There's going to need to be telluric correction that needs to be done. And I need to combine the orders. So when pipelines have jargon that they throw at you, it's good to know all of the steps so that you know what has already been done and what needs to be done still for you to use it. Yeah. Okay. And in very few cases, there are spectra that you're going to get where there isn't a pipeline. And this is mostly for older spectrographs. These days, when instruments are created, there's usually money and time allocated to creating pipelines to reduce the spectra. But for some older spectrographs, this is not the case. And so you do need to know the steps, even if you don't need to write the code to do the reduction, you need to know the steps. But there are some tools that can be used to do this. For example, one that I've used before and that you might have used in a different observational class, even for images and not spectra, is IRAF, and there's a Python implementation PyRAF. And so for that, basically it gives you a graphical user interface where you can upload your spectra or upload your CCD images. And then you can, go through the steps, but it has functions written in it for the median combination and the extraction. So you do need to know the steps to use things like IRAF or PyRAF, but you still don't actually need to write the code yourself. Okay. So this is kind of all I wanted to say about the spectral reduction. And so if people have questions, let me know. And if not, I'm going to start setting up the Kahoot quiz. So that'll take a minute. So if you have questions, just write them in the chat and I can answer them before we move on.
So we have to wait the next week. Can we just, I'm free this week. Yeah, if it was up to me, we could have a call tomorrow to get things done.
Okay, great. I don't see any questions, so I will share the Kahoot quiz.
Yes, we don't have any questions right now, Aurora, so I think we can just move forward to the Kahoot.
Great. Yeah, and then I'll kind of see where people are and I can review some things before we move on.
Perfect.
Okay. Great. Okay. So same as yesterday, you can use the game pin, and then I've added 30 seconds onto each. So now each question is 90 seconds. So there might be a bit of a lag, but hopefully you'll still have enough time to answer the questions.
Yeah, just tell me what you need, just tell me what you need from me. I'm free until the trade show, which is at the end of the month.
Okay, I'm going to wait another minute or two since it seems like people are still signing on.
I won't be able to do anything that week, that's just gonna be 1 week at the start of December. Yeah, sure. Yeah, can we set up, let's set up the call right now. I have my agenda open. As I mentioned, I can meet tomorrow if you want. I'm free any day that you want from now until the end of November. That works for me. And then you mentioned that you could also meet later today, talk about the Ozone. Okay, that's fine. That's fine.
Okay, I think that we'll go ahead now since there's 18 people signed on. That seems pretty good.
I have to run soon, but I have a little.
Okay, yep, so this is for lecture 2. And I'll read them again. So what is dark current? It's broken pixels on the CCD. Dark current is cosmic rays that hit the CCD. Dark current is photons that stay in the detector when the shutter is closed. Or it's thermal excitations of electrons when the shutter is closed. I just realized when I read this that the last two are pretty similar. So sorry about that.
So I'll expect an invite to you tomorrow. And we can do the email tomorrow and then stuff that you mentioned before, right?
Yeah, okay, great. Most of you got it, and I think the other ones who didn't get it got the one that I just realized is kind of ambiguous. So dark current, I think, is best described by the thermal excitations of electrons when the shutters close. But yeah, I think photons can be created by thermal emission, and that would also cause dark current. So good job. Okay, how do you remove dark current from your CCD image? Do you divide each frame by the dark exposure? Do you subtract the dark exposure? Do you mask it out, or is it impossible to remove dark current from your CCD image?
Yeah, I mean, I was just trying to, usually not that big of a big deal, okay? No, man, but I think that you did good. I think that it's a little bit difficult to run through a role play without an onboarding if you've never done onboarding before. So I think that you did a good job filling the 30 minutes with actionable items. So I definitely commend you on that. Self-assess though for me. Give me a couple of things that you think you did well, and a couple of things that you think you can improve next time. Yeah. So not do that. Yeah. I think that's a really good point. You don't want to get stuck in those traps. I'm glad that you. I said, call later today go through emails, but okay. What else?
Okay, so to remove the dark current from your CCD, you actually subtract them. We'll talk about, so it's basically pixels that are illuminated when they shouldn't be illuminated, and you have a certain number of counts in each of those pixels. And so to remove that, you want to subtract those counts that shouldn't be illuminated. Okay, so next, what are flat frames for? Do flat frames show you the spaces between orders, the differences in how pixels respond to light? Are they only used for order extraction, or do they show you how the light changes in intensity over time?
Yeah, I mean, the fact that you were able to list out the steps fairly accurately of what an onboarding is without ever doing an onboarding, I think is fairly impressive. And the case study is purposely vague. The idea is that you go into the call and you have to try to figure out how to fill it out. So overall, I think you did well. I have another Zoom right after this, so me and y'all can just go through the feedback that we've been compiling. We'll let you know, but I think overall, man, I think you handled it pretty well. And I'm really impressed that you were able to come up with some type of presentation, not knowing what an onboard is. So, kudos.
Okay, great. Yeah, so flat frames are used to correct for how the pixels respond differently to light. So it seems like most people got that. They're also used for order extraction, but they're not only used for order extraction. So they have two uses. True or false? What causes most of the sky background emission in the near infrared? Oh, no. Okay, this is not a true or false question, so we'll just skip this one. Okay, it's supposed to be a quiz. What causes most of the sky background in the near infrared? OH emission lines, light from the moon, scattered light from the sun, or city lights?
Yeah. I used to do these back in the day, so I think the self-assessment honestly is the best thing because you can kind of get in the hot seat, let them figure out what's wrong with you. I think he's good. I definitely see some big weaknesses.
Great. Yes, most of you got it. It's the OH emission lines. And I didn't talk about the moon or anything like that. But what's actually cool about observing in the near infrared is the moon is not very bright in the near infrared. So for optical observations, you do really have to care about what the phase of the moon is, because having a really bright moon next to your source can cause a lot of contamination. But for near infrared, it doesn't actually emit much light. And so as long as the moon isn't covering your source, you don't have to care about what phase of the moon you're observing at. And for all observations, you do want to limit city lights, but it's not particularly strong in the near infrared. So the only one that we really talked about was OH emission. So what is an arc exposure used for? Is it to correct for sky emission, to determine the wavelength solution, to correct for the blaze function, or to correct for telluric absorption?
I think another one of the big issues is that he has a very marketing-centric approach, right? He's talking about, hey, what does your marketing team do? What content are you promoting? But in reality, as a technical consultant, you don't never talk about marketing or content. It's just That's a little bit kind of like, hey man, we really need to make sure that
Yep, so arc exposures, most of you got this, is great to determine the wavelength solution. So the arc lamp is what they call the lamp that has emission lines at all of these specific wavelengths. And you can use those specific wavelengths that have been imaged from the lamp to determine what the wavelength of each X pixel on your detector corresponds to.
if we're honest with each other, you could say.
Okay, so what characteristics do you want in an arc emission spectrum? Do you want many lines that are evenly spaced across all orders? Do you want very few spectral lines, but those that are there are very bright? Do you want many lines that mostly fall on only the edges of the order? Or do you want continuous flat radiation?
I agree. Because like in reality, if he knew all the technical aspects of it, he would still fall into the trap that he did today, which was right off the bat, letting the person know this is his first one.
Okay, yeah, so you want a lot of spectral lines. You want at least a few in each order, and they don't need to be that bright because we don't want them to saturate the detector. So the best answer is many lines that are evenly spaced across all of the spectral orders.
Man, like if you start doing that with clients, you are likely.
Okay, true or false? Ozone stops the transmission of UV light into Earth's atmosphere.
Yeah, they like ask a few times, hey, so what kind of marketing do you use? What kind of tools do you use? The only, I think, give them a lot of active listening techniques. I kept like repeating stuff over and over again. He also kept using a lot of fancy terms, like properties, objects, inbound marketing. I mean, I have no idea what you're saying. But overall, I think he did something really well. I was actually really impressed with the fact that he could pull out the presentation and he like took the time to look through the onboarding documents and look at the timeline. I did. Let me share it with you again. Do you think that this is something?
Yes, so ozone is the reason why it's really difficult to observe from the ultraviolet on Earth because ozone, which is O3, is very opaque at wavelengths that are UV light, so less than about 0.3 microns. So the next question is, what are the main sources of atmospheric or telluric absorption in the visible? Is it H2O and CO2, CO2 and O2, H2O and O2, or O2 and OH?
I'm going to do is all the positive items I'm going to put in blue with a little positive next to it. All the negative items I'm going to put in negative. I'm going to go in and start filling this out with the positives and negatives that we talked about. I also put in some things: start doing, stop doing, and keep doing. So I'll go ahead and fill this out. Feel free to jump in, fill it out as well. Yeah, there's no rush. But I guess one of the big questions I have is, what are our next steps? Is this something that we're going to be deciding collaboratively? Is this something that you're going to be deciding on your own?
Oh, great. All right. I thought this one was going to be tricky because I didn't talk about it all of that much, and I did talk about OH, but OH is emission in the near infrared, and H2O and O2 are the two main absorbers in the visible spectrum. So there's some H2O bands around in the red regions of the visible, and then there's two big oxygen O2 bands in the visible as well. So why are A0 stars good for correcting telluric absorption? Because they have few absorption lines, because they are bright and easy to observe, because their emission is mainly black body emission, or all of the above.
I agree. I think he passed the bar of a junior. If this was a technical consultant, obviously the answer is no, he's way too experienced. But I think he passes the bar of the junior. There's definitely a lot of work that we need to do to train him up. But I don't think that he is going to be, I'm confident that given the training, he'll be able to at least start some of the basic projects like a month after he officially takes on the people.
Yeah, okay, great. All of the above. So yeah, for all of these reasons, A0 stars are the best ones to observe. They're bright. They don't have very many absorption lines, so they basically just look like a black body.
Right? If he is 100% comfortable with marking on the steps required, the confidence will get there.
All right, last one. True or false? When a cosmic ray hits a CCD, it will cause a large spike in counts at that location.
It's very difficult to be confident. It's very easy to keep confident. But we'll talk about that because I definitely want your input on this. This is relatively involved. I think what we can do for next step is the following. Let's work on getting the feedback sheet done. I'll set up a call with him and you later on this week. And I think we're both in agreement that he passed the bar. You should bring him on the team. But knowing full well that there's going to be a lot of work that needs to be done before he is officially on it. Yeah, no, I'm 100% sure. He seems like he's willing to put in the work. It's just that he needs to shake off those like that first job jitters, I guess I would say. All right, so yeah, let's get that feedback sheet done. I'll work on it right after this, and then I'll also set up a call for me and you and him on Friday this week. Yep. Yeah, exactly. I'll set up like a call at 1 o'clock. Simon. I appreciate the help on this.
Yep, so that's true. That's basically what happens when a cosmic ray hits the CCD. Is you get a large number of counts, even though those counts aren't from your target source. And so that's another source of noise. All right, and that's it. I like how it does the podium. All right, great. I actually think that went pretty well, except for the one question that I had to skip because I had included it incorrectly. And there's one kind of ambiguous one. But besides that, I think that most of the most popular answer was always the correct answer. So it seems like people kind of understood this lecture pretty well. So I think that there's supposed to be 4 more minutes until the next section. So let me know if you have questions. And if not, I guess we have a longer break now. And I wanted to say before we go to the next break that for the demo today, I wanted to finish the HARP spectrum that we didn't get to do last time. I kind of half showed it to you. And so because some people, or I guess most of you don't have accounts on ESO, and so you couldn't download the spectrum. And so I downloaded it and uploaded it onto my GitHub page. And the rest of the spectra that we're going to be using today are also on my GitHub page. And in the worksheet that was sent out yesterday for today's workshop, it has the link to the GitHub page, so we can do both. Hopefully we'll have time to do both the rest of the HARP spectra today and also what I had planned for today. And one other thing, for today, we're going to be looking at CCD images. And to do that, you're going to need DS9 SAO image, which is an application. Also on the worksheet, it says what the website is that you can download that application onto your computer if you don't already have it. It's a very easy thing to download and set up. But if you don't have it, if you could download it within this 25-minute break, that would be great.
Okay, so thank you very much for the lecture of today. It was really insightful. Please keep in mind that you need some tools for the lab hours that we will have today. So please try to download the data, download the software you will need, and we will see you in 25 minutes at 10:25 Colombian time, 4:25 EU time. So thank you very much and see you in a while.
Yes, thank you.